So today we're going to do another example of finding an eigenvalue, the eigenvalues and an eigenvectors for a matrix. So let's just connect back to solving a system of first order equations because that's going to be our goal in chapter 6. So in order to solve a first order system of equations, we assume that our solutions look like x equals v times e to the lambda t, where lambda is an eigenvalue of A, the matrix A in your system, and v is an eigenvector. So to find the eigenvalues, let's recall that we solve the equation given by the determinant of A minus lambda I equals 0. We solve that equation for lambda, and that gives us our eigenvalues. And then to find the eigenvectors, for each eigenvalue, we'll solve the system of equations A minus lambda I times the vector v equals the 0 vector, and we'll solve that system for v. So that's how we find the eigenvectors. All right, so let's go through another example. So let's find the eigenvalues and eigenvectors of the matrix A given by 4, -6, 3, -7. So here we're finding the determinant of the matrix A minus lambda I. Now the easiest way to write down A minus lambda I is just to subtract lambda from the elements along the diagonal. So that's all you do here. Then we take the determinant, we multiply these two terms together, subtract the product of 3 and -6. So we have this product minus 3 times -6. We multiply it out, we'll get minus 28. We'll get a 7 lambda. We'll get a minus 4 lambda. We get negative lambda times negative lambda gives us lambda squared. And then we'll get a plus 18. And when we simplify, we have our lambda squared term. We have 7 lambda minus 4 lambda gives us 3 lambda. And then a -10 because we have 18 minus 28. So this is our characteristic equation, just like when we solved second order differential equations. Can we factor it? It looks like we just get lambda plus 5, lambda minus 2, because 5 times lambda minus 2 times lambda gives us 3 lambda. 5 times -2 is -10. So what are our eigenvalues? -5 and 2. The order you write them down in doesn't matter. And so let's relate it back to what we studied with second order. We have two distinct real eigenvalues. These are going to be quadratic because we're going to focus on 2 by 2 systems, and so you're going to see a lot of similarities between what we're doing now and what we did with second order equations. So we have our two eigenvalues. Let's find our eigenvector that goes with lambda equals -5 and the eigenvector that goes with lambda equals 2. So for each lambda, we solve A minus lambda I times V equals 0. So our matrix A minus lambda I for this one was 4 minus lambda, -6, 3, -7 minus lambda. That was from the previous page. So we're going to replace the lambda here with -5. And when we do that, we get this expression. And so we get 4 minus a -5 gives us 9, -6, 3, and then -7 minus a -5 gives us -2. Now again, this is a system of equations, algebraic equations. And these two, you think of them as lines, they're going to be constant multiples of one another. And you can just pick one of the equations to work with. So there's going to be an infinite number of solutions. And so we're just going to pick one of the equations. I picked the second one. Solve that for one of the variables. I said 3 times x sub 1 equals 2y sub 1. Divide both sides by 3 to get this. Now, we can plug in something that gives us a nice whole number. So if I plug in 3 for y sub 1, I'll get 2 for x sub 1. So my eigenvector and eigenvector, there's an infinite number of them. So as long as you come up with a constant multiple of the one I have here, you're also correct. So my eigenvector that corresponds to the eigenvalue of -5 is 2, 3. Do the same thing for the other eigenvalue of 2. So again, here's my matrix A minus lambda I. I'm going to replace the lambda with 2. So I get this expression. 4 minus 2 gives me 2, minus 7 minus 2 gives me -9. So again, these two rows, if you think of it in terms of matrices, these are just constant multiples of one another. So just pick one of the equations. I picked the first one. I solved it for x sub 1. Dividing by 2, I get x sub 1 is 3 times y sub 1. Pick a number for y sub 1. There's an infinite number of correct answers. I let y sub 1 equal 1. So if I plug 1 in for y sub 1, my x sub 1 turns out to be 3. So this should be a 3. And there we have the eigenvector that goes with the eigenvalue of 2, 3, 1.